Hello everyone, welcome back. Today in this lesson, I will start first by giving a small intuition about what we have been doing so far. And let me give us such an intuition. And why I chose to talk about of this one in this lesson, because I want you to see what XT and Fourier transformed version of them means. Okay, so let us start. If we have a cosine function, for example, cosine function, let me draw it like this. So in here we can see that this specific function has a specific frequency, right? It has just one frequency, let's say. I couldn't draw them with equal intervals, but let's assume that they are, and it has just one frequency, all right? And what we were going to do is, while showing it in frequency domain, the frequency, and we have the magnitude of the function here in the y-axis. It is the magnitude, all right? We will come to more details, but it is important that we know it right here. And here we will show in frequency domain in two places. It is, we have f1, which is the frequency of this wave, and then we have the negative version. So you might ask, what is the negative frequency? Well, it is a concept which is visualized by angles. So it is, you might be confused with negative frequency, but it is actually related to angles and how it sweeps through the unit circle. And so it is actually, that's it. This is the representation in the Fourier transformed version. In the Fourier transform world, as we are going to represent the time domain functions in frequency domain functions, and this is how we can represent it. Now, let me show you another example. For instance, if we increased the frequency, and we have such a graph right now, what happens? We have another function, let's say, which is called z, and then we have the cosine 2 pi f2t, right? Because it has a new frequency. That's why I called it f2. And then when we are going to show it in the frequency domain, we are going to write here the magnitude of the z components, and then here we have frequency, and then we have a higher frequency. That's why I'm going to write it here like this. As you notice, there's more distance from the origin, so it means higher frequency. And then we have f2 here. Now we have negative f2, the negative of it. And then let me ask you, what happens if we have another function? Let's say if it wasn't cosine, but it was sine. And what would happen? It would, let me show you real quick. It will start from 0. And then let's say that these two had the same frequency. All right. And then let's call it a w function, and then it is equal to sine 2 pi f2t. And then let's find the frequency domain equivalency, let's say. And in this case, I will write the magnitude. And since the frequency is the same, we will have the same graph, right? Now, you might be asking, how are we going to separate these two functions if they are in fact different functions? One is cosine, one is sine, but we have the same frequency domain graph. So how can we differentiate them? In that case, we will use the phase plots, and we will use the property that sine and cosine can be expressed in terms of a exponent of e, and we will have a look at them afterwards.
Negative frequency.
And here I also want to show you, if we have another function like this, we might have a combination of different frequencies, such as like this. Now, let me explain you about the phase that I mentioned here. Here, we can write this sine wave as such, right? 2 pi f2t minus e to the power of minus 2j pi f2t. And I will write this expression a little differently by multiplying both the denominator and denominator by j, and it will give us minus 1 over 2j, and this one can be represented in polar coordinates as e to the power minus j pi over 2. Let me show you here the reason. Minus 1 over 2j, 1 over 2 times e to the minus pi over 2. Here we have 0. Here also it will give us 2 pi. Here we have pi over 2, minus pi over 2. And when we go minus pi over 2, it will give us, here is the imaginary axis. So we will have minus j, and since we have multiplied this by 1 over 2, we still have the 1 over 2 coefficient. So this was just a part to prove you that these two are the same in polar coordinates when we consider the polar coordinates. Anyways, what I wanted to tell you is that now let me show you, if we are considering the positive frequency, then the phase is negative pi over 2, right? Now let me show you here. We have the phase of the w function, and here we have the frequency. For the positive frequency, the phase is minus pi over 2. And similarly, if we do the same calculation, we will see that for the negative frequency, the phase will be positive pi over 2. And this is what differentiates sine wave from cosine wave. Now let's move on and see a little example where this Fourier transform and the frequency domain is used. It is used basically in filter designs. Let me go to a new page and write example filter designs. So let's assume that you are in a park and you are filming a video, and the software that is filtering your voice from the bird's voice gives you a more accurate representation of what you are saying. What I mean is when you have the filter on, then your voice is more dominant in the video recording that you're taking. However, if you turn off the signals, the filters, then you will notice that a lot of bird or other noises will be hearable in your recording. Now, how is this possible? Now, the recorder actually records us and the the time it is the time domain function, and it has a wide variety of signals. This one includes our voice and then other birds' voices, etc. Sorry. And however, what we are our voice has a limited frequency. Our voice's frequency is, for example, like this, has a specific range which is in 3 kilohertz, for example. However, when we add up all the noises of birds, of our voice, of other noises, etc., the frequency range becomes a much wider range, and we have higher frequencies, we've got lower frequencies, etc. And if we apply a filter, which is a low pass filter, for example, which allows to pass frequencies, for example, until this point, then what happens? We will have the frequencies until a specified point, and um, the video recording in the video recording we will only hear the summation of our voice and a small also a small amount of other voices. And it is true that in this part also there are noises of birds, etc. It is true, but it is also true that we have eliminated all this part, which makes our recording much more friendly and much more clear to hear. So eventually we will hear still the noises, however um, in a much lower level, let's say. Now let us move on to a different style of examples. Example, it asks us if the function xt equals to e to the power of j omega naught t, then what is the Fourier transform of this value? Now here, notice that we cannot use our good old formula. Why? Because it doesn't have the sufficient conditions. What were they? That the function should be in we should be able to integrate its absolute value or its square absolute value. Since it is not it does not converge, we need to use another technique. What are we going to use here? So how are we going to find the Fourier transform if we cannot use our formula? Now let's assume that the Fourier transform of x dash omega is equal to delta omega minus omega naught, all right? And so this is the Fourier transform of x dash t. So if we apply the formula, we write x dash t equal 1 over 2 pi from minus infinity to plus infinity. We have the Fourier transform, which we assumed that it was x dash omega e to the power of j omega t dw omega, all right? And we told that this one equals to delta omega minus omega naught. And let me write it real quick. And we eventually have this expression, and and then we can say that and by using the property of delta function, here this omega will be replaced by omega naught. And then after doing that replacement, we will have e to omega naught t d omega. And since this one is now a independent coefficient with respect to omega, we can take it out and we can write basically this expression over here. And then since now this integration can be calculated really easily because as we know, here we'll have the delta omega minus omega naught, and here we have the omega, and in omega naught the value it will take 1. So when we integrate it from minus infinity to infinity, it will take a value of 1 only at one point, and therefore the area will be equal to 1 only at omega naught. So the result of this equation will be just this expression over here. Therefore, here we can say that the Fourier transform of e to the power of j omega naught t over 2 pi is omega delta omega minus omega naught. However, we are asked to just to find the Fourier transform of e to the power of j omega t, and in order to do this we are going to multiply both sides by 2 pi, and that is what we are going to do. So we can see that here the Fourier transform of e to the power of j omega naught t is actually delta omega minus omega naught times 2 pi. So let's make a related example, which it asks us to find the Fourier transform of cosine omega naught t. So here what we need to pay attention is that cosine omega naught t is not an absolutely integrable signal, and hence we cannot use the formula of Fourier transform. So we cannot use our good old formula because, let me write it here, cos omega naught t is not an absolutely integrable signal, is not an absolutely integrable signal. So we are going to use something else. What are we going to use? Now, it is time to use what we have learned in the previous example. Now let me write cos omega naught t equals 1 over 2. This is the old formula that we used to apply, and we already know this equality, right? And now, in order to continue, we are going to take the Fourier transform of each item over here. Fourier transform of this, and then we are going to take the Fourier transform of this expression. Now let me do it like this. Use the same notation overall. And also the Fourier transform of the last item, right? And now we are going to use what we have learned in the previous example. As we know, the Fourier transform of e to the power of j omega naught t is equal to this expression. So what is the Fourier transform of this? 2 pi omega delta omega minus omega naught plus similarly, as we have negative here, we will have positive inside delta, 2 pi delta omega plus omega plus is not, sorry. And then let me write the rest. And here we can take the 2 pi outside of the parenthesis. And here we have our answer. The Fourier transform is simply equal to this expression over here. And we are done also with this example. Thank you very much for listening to me and have a great day.